Okay, got it. So today I'm trying to talking about my recent studies and also my thinkings around how people can better collaborating with AI and more specific biomedical AI through visual explanations and interactive guidance. And yes, I'm Wang. I'm currently an assistant professor in the University of Minnesota, the Department of Computer Science and Engineering. So I guess I don't need to emphasize it again that we are living in the new age of AI. Every day we see some new advancements, AI techniques. We see some like new benchmark performance. And with all those more and more powerful AI models, and especially those like giant large models that are pertrained on a huge amount of data, we have seen many promising applications on the biomedical domains, including how can they help people to treat new disease, develop new drugs, and provide better and accurate diagnosis. So with those powerful AI systems, it's very naturally that we are expecting people would be happier. However, the truth is that more powerful AI systems does not guarantee better human AI collaborations. Sometimes it often leads to more complicated interactions and more frustrated users. Here is a fun example. When GPT-4o first came out, I just tried to search on social media about what people are using it for. And here is one example I found. So some people try to use GPT-4o to generate pictures for the pets. And sometimes it works pretty well. It generates a cute pictures of a little girl who do somehow similar to the pet pictures you uploaded. However, even for this looks like well-defined task and using exactly the same prompt instructions, some people get much weird results, like some old man looking at you in weird positions. And this is not a single case. The frustrations as widely exist in the collaboration between humans and AI, and especially in the current large language models. In a recent study that published last year, researchers found that more than a third of the users will just give up the conversations with ChatGPT due to the dissatisfactions of the results. Some of them will try to solve the issues using simple actions like repeat the same instructions again, or try to do some small modifications of the prompt. As a result, there are more than 72% of the issues will remain unsolved, and just making those collaborations with those powerful AI systems super inefficient. And this is not the only issues that humans have when interacting with AI. Because of those frustrations of collaborating with AI, is deployment in the real world can be problematic. There is a new story about Apex AI algorithms. Also, for some background information, Apex is the largest electronic healthcare provider in the United States. And some recent news found that its AI algorithms are continuously delivering inaccurate information to the hospitals. And those errors haven't been noticed for a long time, and partly because the way people are currently collaborating with AIs is not effective and not efficient. So with all those frustrating collaborations with AI, as a researcher, we want to understand what are the reasons behind those frustrations and how can we better solve them. And here is my hypothesis. If we're looking at the traditional machine learning algorithms or AI systems versus just new generations of AI, which is especially focused on the large language models, we'll see some like clear difference regarding how humans interact with it and how we use it to solve tasks. On the left side, we see how the traditional models work. We typically have a very structured input and output. So for example, we want to use AI systems to do image classifications. The input will be pictures of specified size and also have like a relatively clear context. So you may either have a cat in it, have a dog in it. And then the output is also where clarified, like structured. It's typical if it's a classification, it's just like a list of labels. The models will choose from them. And at the same time, if you're looking at those new generations of AI, the inputs and outputs are really free form. They do not have a clear structure, and they are like super customizable and flexible. People often use it as an iterative process to try to communicate with the AI and iteratively improve the results they want. So you can see here is an example I found from I think the GPT website. You can upload a picture of your own cat and by doing step-by-step promptings, finally ask it to make a video game where your cat is a main character. So you can see here, it's not like the new generation AI is bad so that it needs to frustrate human AI collaborations. But indeed, because it's more powerful, it's able to solve more complicated tasks. And those complicated tasks lead to these frustrated human AI collaborations. Then the next questions would be, how can we facilitate users in those complicated human AI collaborations? Fortunately, handling complex information and process is not a new problem for humans, and it's also not a new problem in the biomedical domain. Many methodology has been developed in the past to facilitate this, to help solve this problem. And among all those different techniques, my personal favorites is thinking scaffolds. So here is a definition of thinking scaffolds. They are tools that externalize, structure, and guide human reasoning. Okay, what does those mean? Let's see some examples. So one widely used thinking scaffold technique is to use whiteboard and sticky notes to help people externalize the ideas and then organize those fragmented thoughts in a physical space, which means like a whiteboard, and then iteratively refine and structure them. And here, those whiteboard and the sticky notes help people to externalize all those different things they have in mind and better structure and them in a physical space. Another commonly used thinking scaffold is checklist. It helps people to break down complex tasks into manageable steps so that it can reduce the cognitive overload and ensure important details are not overlooked. And that is currently a technique that are often used in the surgical rooms. And these techniques can also be used to improve the human AI collaborations. And very natural way to apply it is to help people better write input for the AI systems. So, for example, instead of asking people to write a free-form text and to describe what they want, we may have a better interface that provide structured input fields to decompose all the requirements into small steps so that people can just fill in those small steps one by one and have better descriptions about what they want the AI to do. And even more, we can help the people to understand what they want to do by converting unstructured input text into interactive widgets that are structured, that has a clear definitions, and that humans are getting used to press the intent. So I hope those examples somehow demonstrate the usefulness of providing scaffolds to help people better express and even understand what they want when they are collaborating with AI. However, we're only addressing a small step of the whole human AI collaboration process. Let's say even we have very successful scaffoldings at the input stage and enable humans to express to have more accurate and structured input to help the AI generating better results. We're still having many remaining issues, such as how to help people reasoning through the pronoun and often flawed outputs from the AI, how to help people understanding the underlying mechanisms of the AI generations, and how to enable humans to collaborate more effectively with AI to refine the outputs and to make it more desired and to improve its performance. So when we're talking about problems that I need to present and interact with complex information, in my opinion, interactive visualizations is one of the best solutions. It helps people to make sense complicated informations in an efficient way and provide a space for people to represent these thinkings and convert them into feasible actions in a user interface. And specifically in my research, I try to combine explainable AI and interactive AI with visualizations to help people better collaborating better understanding and collaborating with AI. And specifically in this talk, I will try to understand and solve the three types of complexities during the human AI collaboration process. The first one is how can we help people to better reasoning the AI outputs? The second is how can we help people to better understanding the AI mechanisms? And eventually, how can with a good understanding of the AI outputs and AI mechanisms, how can we help users to iteratively refine the AI results and even the AI model itself to have a better performance and a better collaborative experience? And now let's go through them one by one. So the first thing we are talking about is how can we help people better reasoning about the AI outputs? So if you read the current AI papers, you might have a feeling that reasoning output and the results is not challenging at all. When those AI papers report the output, they turned to looks in so easy. They will just report performance on the benchmark testings, and it's either right or wrong, and they will always give you a number to report how good or bad it is. And when they demonstrate, okay, this is a good AI because it has good scores on the benchmark systems. But if we are actually using the AI systems in our daily activities, and I think you should all be related when you have conversations with current large language models like GPTs or Gemini. The output is just so complicated. Here is the response from GPT when asking him to give me some candidates for drug repurposing for Alzheimer's disease. And this is like only a part of it's like super long and complicated output paragraph. I definitely cannot just take and use this prolonged out this prolonged paragraph. It takes expertise to digest the content, verify it, and identify the improvement required, and then adapt it to the user's original task. And all those things is not easy. And to make it even more complicated, those prolonged outputs often have unexpected hallucinations. AIs are tend to generate inaccurate content, and that looks super misleading. So in a paper that we published last year at WAIS 2024, we try to understand how can we provide better scaffold and to help people digest and reasoning those AI output in the task of information thinking. And specifically, we try to compare it with original way that people do collect and search informations. So if you're thinking about original ways that we think informations, we often use search engines like Google. And all those informations can be directly inspected and interpreted and compared with large language models. All the knowledges are from the training data, and then they are encoded in the form of model parameters, which makes them very hard to inspect or try to verify whether they are true or false. Then our questions become, what if we can use some external knowledge base as a scaffold to help people reasoning the AI outputs? Just similar to how we use search engines, but have direct access to the original data, we should be more confident and more effective to reasoning the AI output. So this is a new idea. This is not a new idea, and that is actually just like a super popular research field around the retrieval augmented generations. The original idea of the retrieval augmented generations is that instead of just giving the questions to the large language models, and which will need to some imperfect response from the AI, we will involve some external knowledge base. For given questions, we will first try to find relevant information about this question from the external knowledge base. And then the model will have access to both questions and those relevant informations. And by doing that, we are able to have better response from AI with fewer mistakes. And that is very helpful, but still we can get wrong response even with the RAG techniques. And here is an example from a recent paper just showing like even with help with external knowledge base, I still generated a hallucinated reference about a specific healthcare questions. And more importantly, RAG does not address the challenges users often encounter when they interacting with large language models, such as information overload, limited support for verifications, or lack of exploration guidance. Therefore, we tend to ask, is the generation stage the only point where external knowledge base can be useful? Could we also leverage it to directly enhance the human-AI interactions? And here is the idea we proposed in the neural nets, guided health information thinking through large language models or knowledge graph integrations. So here we're using health informations and the knowledge graph as a testing bed, mainly because a knowledge graph are attracting increasing attentions in the field of RAG due to the good knowledge representation formats, and also they have those like symbolic reasoning abilities. And specifically in the knowledge graph, nodes are represent medical entities such as drugs and disease, where edges are indicate relations among those entities, which are extracted directly from the scientific literature. They are providing like more accurate information. So here we can say we actually have three formats of knowledge if we try to use the knowledge graph to help people reasoning large language model outputs. So first we have humans who process information in weird and often unstructured ways. We then have large language models who generate a names paragraph, and then we have knowledge graph, which propose a structured topological format of the knowledge. And they're all very different. But how to merge them together? So to address these issues, we utilize the knowledge graph to scaffold a step-by-step information collection process, where users actively and progressively constructing a knowledge graph centered around the object of interest. So here is an example. If the user query about which supplements may benefit Alzheimer's disease, NoNet respond with a node-link diagrams to illustrate the connections between two dietary supplements and the disease, along with the corresponding texts that are generated from the large language models. So users may have some following up questions about why vitamin E is helpful, and the node-link diagrams will update to include new information about vitamin E mechanisms, also extracted from the large language models, and then double-checked with the knowledge graph. And this process continues as users add additional questions and better enhance the understanding of the whole problem. Also, based on these formulations of the knowledge, we can further provide information validations using the literature contained in the knowledge graph. So, for example, here we have the information extracted from the large language models, and then we combine it with the similar information from the knowledge graph and see whether it's validated or not. Additionally, we can also merge user conversation histories with the relevant subgraphs to offer personalized next step recommendations. And this approach builds on the widely accepted assumptions that a concept within the current interest are more likely to be relevant to the user's next step. Okay, now let's say how NoNet integrates knowledge graph to create an enhanced human LLM interface.
To enhance next step recommendation.
Sorry, here we go.
To enhance user experience, NoNet offers two key features: information validation and next step recommendations. Information validation helps users verify the accuracy of the LLM responses. Next step recommendations are provided based on the current exploration and the structured knowledge in KG, guiding users to a comprehensive understanding of their topic of interest.
Okay, so here are some technical details about how we do the implementations. We certainly do not have enough time to cover all those details, but here is an overview of the whole system. So when users ask questions, we first collect response from the large language models, and then find relevant nodes from the knowledge graph. By matching them in a shared embedding space, we can produce a text output along with a node link diagrams that including the validation information. And identify the node in the knowledge graph are then used to expand a subgraph, which is then aligned with exploration histories to ranking nodes in the subgraph and creating a recommendation pool. So here we are. We first demonstrate the effectiveness of it using both use cases and expert interviews. And we observe an increase in user trust as users typically hesitate to rely on large language models for critical information. They also leverage both the knowledge graph and the large language models to complement each other. And also witness that the large language models are able to provide more detailed explanations, where the knowledge graph offers more concise and structured information. So NoNet demonstrates that scale fields can be provided by external knowledge resources, and it can be used to facilitate different aspects of the human collaboration by just looking at the AI outputs. It facilitates content digestions, verifications, and next step explorations and refinement. And you can also see there are like two key important components in the NoNet. So first, we want to provide meaningful organizations of complex informations. And second, we want to provide effective visualizations and interactions. But there's still one question that we do not fully answer in the NoNet, is whether the visualization we choose is the most ideal one. We use node link diagrams probably because they are very similar to the default topology structures of the knowledge graph. But as these are one-size-fits-all solutions. To answer these questions, we extend another studies where we try to investigate the impact of explanation formats on users' perceptions of AI explanations. And here we are still looking at the knowledge graph, where node is like medical entities such as drugs and disease. And but the context is slightly different. Here we are training a graph neural networks to predict whether an edge exists in this knowledge graph, which means whether a drug can be used for treating a disease, and it is helpful to even identify new drug repurposing opportunities, which is like reuse existing drug to treat a new disease. And here we demonstrate 3 different ways that one edge predictions can be explained. So we can either explain it using a subgraph, which is surrounding areas around the drug and the disease, or a path-based explanations. That is the paths in the knowledge graph that are connecting the drug and the disease and provide biological related mechanisms to this prediction. Or we can provide neighbor nodes, which is like what are the most important nodes around this drug and around this disease that are relevant and support these predictions. And here is an example about how the node-based explanations, subgraph-based explanations, and the path-based explanations, how they look like for explaining the same prediction. That is, one particular drug, repaclite, can be reused for treating the Alzheimer's disease. And of course, we will need to build some new XAI algorithms to support the generation of different explanations, but we will not delve into all details here. And you can see all those explanations are quite different. But how can we know which one of them is the best for understanding the explanations, and especially for the domain users to better use it to collaborate with AI? So Here is our hypothesis. We hypothesized that when an explanation is mostly similar to how the human experts would reason about the phenomenon themselves, and when explanations can seamlessly fit into the existing workflows, that this explanation is the most useful for the end users. And based on this hypothesis, we compare those three different explanations to the current way that biomedical experts are reasoning about drug indications. So you can see here is how doctors would reason about why ibuprofen can be used to treat the pain. And this process can be somehow abstracted as passes. Like the ibuprofen is first connected to the cell X, and then to another biological pathways, and then to the symptoms of pain. And based on our hypothesis, it should mean that path-based explanations should be the most useful one. And our user studies do demonstrate this hypothesis is true. So we see that users are able to perform the tasks more accurately, confidently, and quickly when they are giving path-based explanations. Another interesting thing we also observed in the user study is that a poorly designed visual explanation is not necessarily better than a non-explanation baseline. So we can say when users are provided the node-based explanations, the task accuracy and the confidence is almost the same when they are giving a non-explanation baseline, which is like when they only know the confidence scores and the predictions of the AI. And that's the first time we found that for the scientific applications of AI, the design of visual formats can make such a huge difference. And here is a brief use case of how the proposed path-based visualization tool looks like. So users can first choose a disease. We will predict the drugs and also show the predicted drugs in the embedding space. And here are the path-based explanations. Similar drugs form clusters in the embedding space and also can be examined as a group. And we can also see here these clusters of drugs are all anti-diabetic drugs, and this really is like consistent with our current understanding. If we choose one drug from H, we will see the explanations. It's okay. We can, of course, delete something that we think is not very useful. And so, for example, here, the drug is used because there is like a shared gene target, or like a gene is connected to the drug, and which is also connected to a target gene of the disease. And interestingly, we also see that similar drugs in the same clusters sometimes share similar explanations. So the findings and these tools make the communities exciting, and we have several awards. But also something we find is that the better our explanations were, and the more wide questions we have received from our users. And then lead to the next challenges or complexities we want to answer is like, how can we better understanding the AI mechanisms? And visualizing the internal AI mechanism is not actually a new question in the visualization field. It is a classic topic we call wasteful ML, and which has been widely studied, and it try to use the visualizations to represent the internal mechanisms of AI. And here is an example from how we can visualize the internal mechanisms of graph neural networks. But as you can see, the current large language model is much larger and complicated than the previously machine learning models that we have talking about in the context of ways for ML. So those techniques can be also extended to the large language models? The answer is yes, it can. And I think recent Anthropic, which is the company that proposed the cloud AI, has do some like exciting research around the interpretabilities of large language models. So here you can see they first are able to identify neurons or like interpretable features from the model itself. So you can see there are certain features in the large language models that are related to the legal language, which means there were all those features will always be triggered when the input have something related to the legal language. And we also have some like features within the model that will be triggered when the input related to something of the DNA sequence. And those interpretable features not only exist in the large language models, but also exist in like multimodal models, like visual language models, and they can also be and those neurons are also responsible to language from different countries. So here we have one neuron, one feature that is related to the Golden Gate Bridge. And you can see those neurons is actually be triggered or like activated when they give in descriptions about the Golden Gate Bridge in English or like even in Korean and in Russian or like giving them some pictures. And based on those interpretable features within the large language models, we are able to construct a network, like a reasoning pathways within the large language models to demonstrate what's happening when we give it questions and what are the different features that are got involved for generating a final output. So for example, here, when we asking the model was the captains of the state that contains Dennis. And here are the so first we will have features activated that are related to captain, that are related to state, and that are related to Dennis. And based on those features, we will have something related to text, and finally we got the results of Austin. And it also, and to better illustrate those like reasoning process, we can also say if we modify some features, let's say we replace the Texas with China, but we need to try like very hard to make these features have a large activations, we will get a response that it says Beijing. And by doing that, we are actually being able to apply the same techniques that we have did when we're doing the ways for ML to the AI to the much more complicated and larger AI systems. However, if we're talking about biomedical AIs or other AI systems that are targeted as domain experts, we want some visualizations that are accessible for the general end users. And so far, those techniques look like they are primarily focused on AI researchers and practitioners. So can we also support people who have maybe a relatively no AI expertise? And the answer is true. So the increasing popularities of the working flows or like a chain of thoughts in LLMs not only improve its performance on complicated tasks, but also provides scaffolds for the visualizations of the working mechanisms. So some background knowledge regarding what is a chain of thoughts. So when we're talking about the previously interactions of the large language models, we will just give it an input and the model will give us an output. And when we're doing chain of thoughts, instead of just asking models to give us a single output, we were also asking it to illustrate its reasoning steps that from the input to step-by-step generate the output. And this process can be even more complicated by using tree of thoughts, which means instead of providing one linear reasoning process, we may have multiple reasoning process and then dynamically decide which reasoning is more reasonable or meaningful. And so by visualizing those chain of thought process, instead of reasoning the complicated interpretable features and the training with, the end users can actually access to the design behind large language models and observe its authentic reasoning process. And here is an example from a Kai paper. So you can see without the chain, we were just giving the input and generate the output. However, with the chain of thought, we can have a more detailed reasoning process of like why the AI is doing that. So here we have the original feedback about Alex's presentations, and we want to make it more friendly. So in a chain of thought, we will just first split the points in the original feedback, try to make each of them more friendly, and then compose and merging. It provides more transparencies and also controllabilities for AI systems. And this is also what we are doing in a white paper we published this year, 2025. So we are able, by presenting the large language models underlying reasoning process into a hierarchical presentations, will enable users without AI expertise to better understand AI and even compare different algorithms. Okay, so far we have discussed how we can use visualizations, scaffold, interactive guidance to help people better reasoning the AI output and understanding its underlying mechanisms. And it's definitely help people to better use and collaborate with AI. However, to truly achieve our goal of great human AI collaborations, users eventually need support in refining and improving AI. Like we do not have a perfect AI algorithms, and also like our context of using AI, our requirements and our user needs changes all the time. So those refinements is definitely very important to produce desired outputs from AI. But this process is typically very challenging. Again, let's thinking about a conversation with large language models. You give it a picture and it said it's a tiger. Okay, you know AI is wrong, so it tells you, okay, no, it's a cat. Okay, great. Now it understand the image is not about a tiger, it's actually about a cat. But next time, if you give it another pictures, it might still making the same mistakes over again. And that's just illustrate the current frustrating AI refinement process. We may able to fix individual outputs, but they often not provide a generalizable knowledge for the AI to systematically update its knowledge. And I would say this is like the problem of lack of generalizable knowledge from the users. Then the question would be, how can we provide efficient and effective support to help users provide those generalizable knowledge and to better refine AI systems? Let's start with a simple question, or simple problem with the typical classification problem. AIs can understand and class different classes by using the knowledge they learn from the training data set. However, if we are thinking about the implementations in the real world, when we deploy AI systems, the new data or like those unlabeled data, like those like circles, the wide circles, they are not necessarily looking very similar to the data the model has already seen and learned in the training data set, even if they are from the same types. And this is something we call the batch effect in the biomedical domain, especially in the single cell field. And the problems is that, so definitely we can provide some fixed automatic refinement or like fix, but this problem is that AI may not be able to tell technical variance, which is like a batch effect. Those cells are indeed from the same type, but because they are tested in different labs using different devices, so the result, the values need to be different. Or because they are truly biological variants, which means they are indeed different cell types. So the current way people fix these problems is to manually label some items. However, as we have discussed before, that is not a good way to provide generalizable knowledge. And also, users do not want to be treated as an oracle that simply label individual items one by one. And they also find the transparency of the AI systems is very important to help them provide accurate feedback. And that's why we propose a new interaction called anchors, which is which exists like two clusters of items. One cluster is from the training data set, and one cluster is from the testing data set. The one from the training data set is anchors from the one from the testings because they will be giving the same labels. It is helpful to help people better understand why the predictions on those new items are made because they are based on the similar clusters from the training data set. It also helps people to steal AI by, let's say, approve or reject individual anchors, and then which will be used to update the system. And these anchors provide a scaffold for providing like a more generalized for users to provide more generalizable knowledges instead of saying like individual cells like one by one that they are from a specific cell type. One user's actions actually can be applied to a group of similar items, and that can be generalized and to improve the model performance. And in Polyphony, we implement these ideas. So we first identify clusters from the testing data and then matching them to generate anchors. And you can see in the visualizations, anchor is represented with one clusters of dots that are from the testing data set, and then another clusters that are represented with grid that are from the training data sets. And this edges indicate the difference between those two clusters. We also provide the ranking of all the anchors we detected and also explanations of like why one anchor is generated. And so here is a demonstration how we select one anchors and modify it. So I can say, based on from those anchor-based refinement, we're able to generate better results that with fewer differences between the training data set and the testing data set. The model's performance has also got improved with those anchor-based user feedback. And you can also see that instead of accepting all the recommended anchors, the user enrollment achieved the largest performance by only selecting the most high-quality anchors. So in the polyphony items often form clear clusters based on their overall similarities and after the dimension reduction. But we often see datasets that do not have clear clusters, and the user may interest in a certain aspect rather than overall similarities. So for example, here we have patches of the breast cancer specimen, and we can see there's no clear clusters in the embedding visualization. And that's how we propose concepts to help people better represent the knowledge to the AI models. And here a concept is more flexible and transferable knowledge than the classes. It can be used to describe the characteristics of items such as shape or texture. For example, here zebra is related to concepts of horse, stripes, and the grass. And in the example of the breast cancer specimens, by enable users to provide the concept they are most interested in, we're able to present and organize those items in a more meaningful and interpretable way. And in our study job, we try to build systems to implement a 3-step workflows to help people interpret the concepts, analyze the concept with humans, and then generate new knowledge from those organization of items based on concepts. And we will not have time to go through all the cases. But here is results. So the orange line is ours and the blue line is from active learning system. So you can say by allowing users to provide concept-based refinements, the models are able to achieve more higher accuracy with fewer user inputs. So in summaries, I'm trying to understand how can we better facilitate the human collaborations with AI and maybe more specifically on biomedical AI using visualizations as a thinking scaffold. And we're basically trying to solve 3 different challenges regarding how to help people reasoning about AI outputs, understanding the AI mechanisms, and also iteratively refine AI outputs, and also maybe the AI model itself. And all the studies we have discussed in this paper have open source documentations, demos, and real-world users. They will also have some media coverage. However, that's not the way I want to finish my talk. I want to finish my talk with a questions. So far, we have said about by providing visualization scaffold, we can help people to better reasoning AI output, understanding AI mechanisms, and iterating refine AI systems. But do humans interact and collaborate with AI as we expected? The answer is it depends. If we're thinking about just like a very simple applications of how humans writing with AI, which is now increasingly popular in those days. The interaction process is like super messy or unstructured. Humans might jump from like different states, like text productions, citation integrations, forth and back. And for example, here might be an ideal way how we want humans to write with AI. So all the orange part is like writing by humans. The x-axis is time, the y-axis is a writing progress. Humans have a stable speed of writing, and they are open AI suggestions sometime. This is also like a good ways of how humans correlate with AI, some frequent interactions within a short period of time. However, we also have people who basically using AI all the time during the writings, or people who just don't even open AI at once during the whole process. And all those actually from the real user stories data. So, and this is the question I want to end with my talk. Even though by providing visual explanations and interactive guidance is helpful and essential to facilitate human AI collaborations, it must be grounded in a comprehensive understanding of the underlying human behaviors and of the human AI collaborative dynamics. Okay, and that's all. I also want to thank all my collaborators and the students to making those studies possible.